We will be discussing probably the most important physiological principle when dealing with neural action or neurons, and that is what we call potentials. And the potential that you'll hear talked about the most will be what's called the action potential, which is third on our list here. Now, potentials mean a potential change of voltage within a cell. We know that one of the big subjects so far has been the movement of ions, sodium or potassium or calcium, whatever, mainly sodium and potassium, but the movement of ions across phospholipid bilayer membranes. So we know ions are charged, so we also know that we try to keep a neutral charge inside of a cell. But in reality, right next to the phospholipid membrane on the inside, there's usually a negative charge and a slightly positive charge on the outside of the membrane. So we're going to talk about that, and I'll show you some examples, but we are going to be talking about three potentials. Again, the last one we will talk about, but the one that we've probably heard the most about is the action potential. And another name for the action potential would be something like a nerve impulse. But before we can have an action potential, we need to understand what a resting membrane potential is and what a graded potential, because all three of them are involved, and especially these first two are involved in helping create the last one, which is the one we will spend the most time on. Okay, we will come back to each of these, but let's start out talking about what a potential is to begin with anyway. So here we actually see a neuron. Here we see the dendrites out through here. We see the soma, also called the cell body. We see the axon. It happens to be myelinated, and that actually speeds up the signal in a process called saltatory conduction. We don't really see the very ends of the axon here, but we will discuss what's going on there. The ends would actually look like this thing right here and this thing right here can be branched out many times. So what this area and this area is they're the ends of other axons from other neurons. All right, notice we do have the term excitatory and inhibitory, and synapse is actually where the neurotransmitter is being released from one neuron to another. Okay, so we'll get into the difference between what's going on with an excitatory and inhibitory a little bit later. But right now, let's look at our setup and our graph here. It's really important to understand this. And so the first thing, notice our numbers, and this line of our graph is representing our voltage, which is measured in millivolts. So that's 75 or negative 75 millivolts, negative 65 millivolts, negative 40 millivolts, negative 20 millivolts, 0 millivolts, and then finally positive 20 millivolts. So notice that this line right here with the dotted line is marked resting potential. So going back to our very first page, notice our first potential we're going to talk about is the resting potential. Now, it's called resting potential because if we were to measure just inside the cell membrane on this particular cell, if we were to measure the voltage charge, we would get a negative 65 millivolts. And that's when nothing is happening, because we're basically saying the cell is at rest, so we have a charge of negative 65 millivolts. All right, so now different cells have different resting membrane potentials, or resting potentials. You can say it either way, RMP, resting membrane potential, or just resting potential. Some cells will have a much different number than negative 65. So all cells have their own resting membrane potential, but the cells we're mostly concerned with will be neurons and muscle cells, I guess would be the two cells that we would talk the most about resting membrane potentials, but every cell has one. All right, so for this, you'll normally see this around negative 65 or negative 70 when we are speaking of a neuron. Now we'll also see the cardiac muscle cells will also have their own resting potential, but we'll get to that later. Now, if nothing is happening and we measure just inside, we would come up with a measurement of negative 65 millivolts. But if we actually have an excitatory signal, which we see here, an excitatory signal, and what an excitatory signal would do would be to allow the neurotransmitter would open up little channels that allow positive ions to come in, such as sodium or calcium or whatever we'd be talking about. And we'll get into the specific ions later. Remember that the neurotransmitters actually serve like little keys opening up doorways. The doorways are the proteins in the cell membrane that are allowing ions to come in. So again, if we have an excitatory signal, an excitatory synapse, we're opening up doorways that are allowing positive ions to come in. Now, we also have inhibitory synapses, and what they're going to try to do is inhibit the signal, or instead of positive ions come in, we're going to try to actually allow positive ions to go out or negative ions to go in. Now notice, if I'm in debt and I either keep spending money or have bills come in, then I don't get out of debt, I get more in debt. So the inhibitory signal, again, is caused by neurotransmitters that open up doorways that either allow positive ions to leave or negative ions to come in, thus making me more negative. Okay, now if both of these are happening at the same time, in other words, I have excitatory synapses that are the excitatory signals opening up gates that are allowing positive ions to come in, and I have the inhibitory synapses that are allowing gates to open up that allow positive ions to go out or negative ions to come in, then I actually have a combination of the negative and the positive happening at the same time, so I get an integration or an average between both of those, and then my millivolts, this would be the true reading of my millivolts because it would be this signal minus that signal. Now, at the same time, notice that we have another line up here. In this case, it's negative 40 millivolts. That's called threshold. Well, our goal of trying to get excitatory synapses is for our integration line to reach threshold. If we reach threshold, then the next step, which occurs down here at what's called the axon hillock, the beginning of the axon, then this would then trigger the action potential or the nerve impulse down the axon. If our integration never reaches threshold, we may be receiving neurotransmitters, both inhibitory and excitatory, but if we integrate both signals, or we may just have the excitatory signal, but bottom line is, if we never reach threshold, then we never fire the action potential. Okay, so our first potential was our resting potential. That's the measurement we can take inside of the cell membrane if nothing's happening. The next measurements we're looking at right here, whether it's the excitatory signal, the inhibitory signal, or the combination of both of those signals called integration, that is actually what we refer to as our graded potential. So it's the next thing. Now, the graded potential goal is to either reach threshold or prohibit reaching threshold. If we reach threshold, if our integration or just our excitatory signal, if we don't happen to have an inhibitory signal, but if we have both, it would have to be integration. If either one of those situations reaches threshold, then that takes us to our third potential, which is our action potential. This is like the trigger that allows the action potential to occur. Now, let's look here, and by the way, here we have a neuron. Here's our axon. The beginning of our axons are axon hillock. Here is our ends of other axons that are releasing neurotransmitters. Either they're going to release inhibitory or excitatory, and they're going to release them either to our dendrites, as we see here, our dendrite there, or they can release them to the nerve cell body themselves. Now, these action potentials these graded potentials, the positive or negative value that comes in, actually, after it comes in, it starts decaying or becoming less than when it first came in. So this negative becomes less negative. This positive becomes less positive as they get further away from the source where they came in. All right, so here we actually see again the neurotransmitters, which are in these vesicles that are released from an action potential. That's really the whole purpose of the action potential. It triggers the release of neurotransmitters that are in these vesicles. to be released across this what's called synaptic cleft in this area called a synapse. And again, we're looking at this particular situation, and action potential is running down through here. It's triggering the release of neurotransmitters. Neurotransmitters then are causing the graded potential. If I reach threshold with the graded potential, then I send an action potential down this direction from this neuron. So I can have many, many, many synapses where this is synapsing with this. Matter of fact, this is an actual picture. Notice our nerve cell body, or soma. Notice all these synapses from other axons from other neurons that are synapsing with this, either releasing excitatory or inhibitory neurotransmitters. Now, at the synapse, again, here's the vesicles within the bulbs of the axons, and they're causing an exocytosis or release of a neurotransmitter. Now again, the neurotransmitter itself does not actually go into the postsynaptic membrane into the cell, but it actually goes onto a protein, and there's one and there's one, and they serve as like little keys to open up doorways, and then the doorways allow ions to come in. Now in this situation, since that ion is sodium and sodium is positive, then if a bunch of sodium goes in, then what it would actually do is we would give us this excitatory signal because sodium is positive. So as it goes in, it's going to build up that going to build up that voltage towards threshold. And then if we reach threshold, we may go ahead and generate what we call an action potential. Okay. Now, so here we actually see sodium coming in because the neurotransmitters have opened. The neurotransmitters were released from the presynaptic cell axon. They came down, they opened up these doorways so sodium could come in. Now I'm changing the voltage inside the cell. Now, if this were an inhibitory neurotransmitter, it may allow a negative ion to come in, or it may open up a channel that allows positive ions such as potassium to leave. But because I see it's sodium here, I know that sodium is positive and I see it coming in, so I know it's actually exciting the cell or making the millivolt numbers grow. Okay. And again, we see some examples of that. Okay, now, so notice here at our graph again, there's our resting membrane potential, there's our threshold. If a graded potential, which is our excitatory and our inhibitory and the integration between them, reaches threshold, now we get the next step. We actually get the signal passing down the axon in segments, and we call the first part of that signal depolarization as sodium rushes inside. We call the second part of the signal repolarization as potassium moves out. So we go from a positive negative to reverse back and forth. So going from a negative charge inside to a positive inside, that is, notice we're negative here, but when the sodium rushes in, notice we go past zero to the positive. And then we reverse that. So here's the rising phase of our action potential, and here's where we repolarize. So we depolarize it, we take it from negative to positive, then we repolarize it, we take it from positive back down to negative again. And that repeating sequence of positive to negative, back and forth in segments as it runs down the axon is actually what an action potential is. Now, a couple of things here. So let's look at this. Notice that here's the outside of our cell. Here's my channels opened up. And the reason why those channels opened up is because I reached threshold. That is actually a voltage-gated channels, because when I went from this voltage to that voltage, it opened up the channels. Sodium started rushing in, which then caused the depolarization. So as sodium rushes in, sodium rushes in, sodium rushes in, this number grows, 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 and grows. Well, these gates are timed, so they actually start closing, and as they close, then these gates here that are potassium gates, they open up and potassium starts leaving. Well, if potassium starts leaving, we become negative again. Now, this is actually an example of what we call a positive feedback loop, and this is the signature that we get in this thing that happens in the axon which is actually called the action potential. It is a repeating depolarization, repolarization, depolarization, repolarization as the signal moves down the channel in one